Okay, we can start when you're ready. All right, good afternoon. Now, let's briefly review what we did last time, all right? Last time, we talked about how to characterize the interface traps. And specifically, we look at how to find this quantity DIT as a function of energy from EV to EC. What's the density of interface traps near the conduction band edge, in the middle of the gap, and near the valence band edge? And we'll look at the CV technique, as well as briefly something called a charge pump technique. Actually, there's a very nice technique. It's a little more complicated, and as a result, has not been used very often in the last 10 years. But I would like to briefly mention that, and that's called the conductance method. It's not a new method. It's a classic technique, and let me just briefly mention what that is about. All right. Now, if you brought the slides book, you may want to turn to slide 4.8. It's one of the slides from the previous lecture that we did not use. I want to complete that discussion. If you don't have it, perhaps you can just look at the screen here. What it does is it models the MOS system in this equivalent circuit. There's the Cox. Okay, perhaps we can zoom in. The projectionist, can we zoom in on this diagram here? Yes, you have the oxide capacitance in series of two capacitances connected in parallel, and you all know or expect C depletion on one side. The other side is the C interface trap. Is that right? We did not include the accumulation capacitance, did not include the inversion capacitance, because we know that we won't be able to probe the interface traps when we are in strong inversion or strong accumulation, so we're only limiting ourselves to the depletion region of the bias. Is that right? So we have these two capacitance. What's new in this diagram is a series resistance added to CIT. Now, anytime we add a resistor in series with a capacitor, what we are doing is we are introducing a time constant, RC time constant. And this time constant represents the time constant of the interface trap, the time constant for it to exchange carriers with the substrate. So it's the time constant for it to gain electrons and lose electrons. Is that right? Now, we don't know what value that time constant should be. Let's just call it tau. In fact, tau will be one of the quantities that this technique can determine for us. So unlike the CV technique we talked about last time, this technique actually will give us the time constant of the interface traps. All right? Okay? All right. So we don't know what tau is. Tau is something we're going to obtain. But we know R should have the value of tau over CIT in such a way that R times CIT gives us tau. Is that right? All right. So that's the equivalent circuit. Gee, what are we going to do? Now, what we're going to do is we're going to try to make a whole bunch of CV measurement of this MOS capacitor, and as a result, determine two unknowns. What are the two unknowns? One is tau. One is CIT. CIT is useful because we know CIT will give us DIT, right? Remember that? Okay. In fact, CIT is equal to DIT, remember? CIT actually is equal to DIT, Q times DIT. From last lecture, yeah. So if we know DIT, we know if we can measure CIT, we can measure DIT. Now, how can you measure obtain or determine several unknowns out of this CV measurement, well, what you do is you make measurement at multiple frequencies. That way you get a lot of inputs. From that you obtain tau as well as CIT, right? Okay. The first step we do is we redraw this equivalent circuit to simply a parallel RC circuit. We all know we can draw equivalent circuit, right? So if you did that, you will find out the C, equivalent C, is now equal to C depletion plus CIT over 1 plus omega squared tau squared. You do that just by using the usual RLC circuit reduction technique. Yeah, it's okay, nothing special. But what we're really interested in, turns out, is especially useful to measure this resistance or conductance. The conductance has the value of CIT omega squared tau over 1 plus omega squared tau squared. We prefer to work with that rather than with capacitance, because when you work with capacitance, there often is other stray capacitance you have to deal with. That's difficult. Actually, the conductance is less of these stray conductance in a measurement system. All right. So we just found it's easier to deal with this conductance. So what you do is you just put this MOS capacitor on an RLC meter, HP or other manufacturers' RLC meter, and measured R. Throw away the C value, just measure that R, all right, or the conductance, and measure that at several frequencies, omega. If you just look at this expression, you find that if you plot G over omega, against omega, you get this bell-shaped curve. This curve peaks at 1 over tau, at omega equal to 1 over tau, and the peak value is CIT over 2. So just by measuring G and plot G over omega against omega, we get both the tau that we wanted and the CIT that we wanted. Do you see how this works? All right. So it's very straightforward. And you do that, you will be able to find, for example, tau indeed tends to be long near the band edge, and often this data is not even complete because this number may be too long for this technique to work comfortably. Right? It will require measurement at very low frequency. We all know that RC meter, RLC meter have limitations when you make measurements at too low frequency, right? And but typically what's noticed is an exponential relationship between the time constant and the energy of the traps. All right? This is a very nice technique, but for some reason it's not very often used. I think somewhat underused technique to characterize the interface. Okay? Okay. And final conclusion, concluding remark I would like to say, that is when the oxide becomes very thin, all these techniques, well, especially the conduction method and the CV method, are becoming less sensitive to interface traps. The CV method, right, and the conductance method. Reason for that is the how should I make it? How should I put it? This is probably the best way to put it. Is well, I guess that is it is true. Let me think about this. All right, let me just say this. In general, making capacitance measurements becoming very difficult when oxide is as thin as they are today, because there's a significant amount of leakage current. So even if we just want to measure the thickness of the gate dielectric from the CV measurement, we already encounter a lot of difficulty. And now try to get information about interface traps certainly is difficult. So you will see that there has not been much work about trying to characterize interface trap in the very thin dielectric, let's say 20 angstrom or thinner. all right? And although it's a very important problem because we are looking at different ways of very dramatically different new ways of making the gate dielectric, perhaps using nitride, perhaps using other high K dielectric, you find out that we're at the same time somewhat behind in our ability to characterize the interface. So that's an interesting area for research. Are there other techniques that we can do this better? For example, the charge pumping technique perhaps has a relative advantage because that technique is not sensitive to the well, let's say the oxide thickness, but if there is a leakage current through the gate dielectric, I suppose actually the charge pumping tech does not have advantage. As you can see, I'm just thinking through that myself. As I said, this is a new problem that we're running into. That is how to characterize the interface very thin dielectrics where the dielectric is quite leaky. You see, all this analysis assume we have very good insulating dielectric. All right, that's going to be a problem. All right, any questions about what we discussed last time? Okay, if not, let's start a new topic. Yes?
Why wouldn't the time constants be separable? Meaning that even if you have a light leaky dielectric, the time constant of the gate, the oxide, and that leakage, why would you assume that that impedance, that leaky impedance, would interfere with the measurement of a much lower frequency time constant?
I probably don't have a complete answer for you. As I said, this is a new problem even for me to think about. I did not particularly emphasize that measuring the time constant is a problem. What I said is that in general, characterizing the interface trap is a problem. For example, just getting DIT is a problem. Because if you depend on manipulating the detail of the CV measurement, of course, you better have very accurate CV measure to begin with. And when you have a leaky dielectric, it's very difficult just to make CV measurements. All right. So I'll give you an example. Right now, one technique that's proposed to measure the dielectric thickness, not interface traps, just measure the dielectric thickness in the face of leakage is actually to use multiple frequency. Try to model just the dielectric itself, not interface, with very complex RC equivalent circuit. You see, we don't even know with a new dielectric, we can assume this to be independent frequency. You see? You know, maybe Franco-Poole kind of a hopping phenomena. We're not even quite sure how to model the leakiness. So when you are faced with this, certainly I think the literature has not yet gotten to characterizing the interface of these new dielectrics. But this is exactly where we need that information. It's really a problem right now. Okay? All right. So chapter 4, we start a new chapter. We're talking about MOS-IV. 4.1 is a review, and by review, I would like to use this opportunity really just to kind of review what would be typically covered in an undergraduate level of MOS theory discussion. So we'll use this hour for that. But even there, you will see that I'll introduce some twist, all right? I don't think you have any problem with that, but hopefully this will make it a little bit more interesting for all of you. All right. We'll see this first twist in the first slide here. I want you to take a look at this cross-section. We have a gate. We have a inversion layer. Let's just visualize the inversion layer as a very thin sheet of electrons, all right? To the extent it has some finite thickness, we can incorporate that fact into the thickness of this T ox. Is that right? In fact, the subscript E stands for either effective or electrical. In other words, it may not be just the physical thickness of T ox. We might have already incorporated some of the thickness of the thickness of the inversion layer in it, right? And what's the other thing that might have been included in this T-ox effective? Polydepletion, right? So, all right. It's okay. So we're not going to carry those explicitly, but we have to think that this oxide thickness perhaps is more than the physical oxide thickness. So once we have done that, we can visualize this inversion layer just as truly a thin sheet of electrons. Is that okay? But I do want you to remember right from beginning that we do have a depletion layer under that inversion layer. And the thickness of that depletion region is called WD max, right? That's our common. And under WD max is the neutral body. And this neutral body, as some of you know, sometimes is referred to as the backgate. Right? We have the backgate effect or the body effect, for example. And so I want to emphasize that concept. It's a backgate. It really serves the function as a second gate. We have a front gate, we have a back gate. All right? So keep that in mind. For example, just as the front gate can modulate the electron inversion layer charge density with a voltage applied to the front gate, so can the back gate modulate the density of inversion layer charge with a voltage applied to the back gate. You see that? These two things are really the same. They perform the same function. See that? All right. So the front gate has a thickness called a T-ox. The back gate also has a dielectric thickness called a WD max. Right? Other than that difference, the function of front gate and back gate are very similar. So we'll make use of that symmetry, and I think that will give us a useful picture of how to think about the effect of the substrate. All right. There are two capacitors, and there are two charge components, you may say. And so when we look at the Q inversion layer, we have the minus C ox effective. For the same reason, we added this E to the subscript of the oxide thickness. We may carry this E for the C ox just to remind us that we're talking about the effective capacitance, not just limiting ourselves to the physical thickness of the oxide. All right? And after a while, you will see we'll drop this E. It's understood when we talk about the C ox, we already include the thickness of the inversion layer, maybe the polydepletion. Okay? All right. So C ox E times VGS minus VT. That part, I think you have seen 100 times. So won't say anything. All right. Yes, a comment? All right. Now there's a second term. Second term is C depletion times VSB. C depletion, of course, refers to the capacitance of this depletion region, right? Yes? Times CSB is the bias between the body and the source. For now, let's assume source drain are at the same potential, right? So source drain, we don't consider this VDS, source and drain, and therefore the entire channel is same potential. So next slide, I'll add a VDS. It's okay? All right. So VSB. Now, let's look at the sign, okay? I don't want you to worry too much about the sign, but let's go through this once. There's a negative sign here. We already have seen that before. That's because we take the charge at the bottom of this capacitor, but we take the voltage VGS from the top of the capacitor. Is that right? Is that right? Yeah? For this capacitor, it's different. We take the charge from the top top electrode. Yes? We take the voltage also from the top. You see VSB, B being the reference. Is that right? B is the body, is the bottom of the electrode, yes? Yes? S is the top of the electrode, yeah? Top electrode of this capacitor, yes? So therefore, we use a positive sign. It's okay? All right? Okay. So if we collect some terms, minus COXE VG minus parenthesis VT plus C depletion over COXE times VSB. All right? It's nothing new, just collecting terms. All right? Now, if we compare this with our usual expression of COXE VGS minus VT, that's our usual expression for Q inversion. Is that right? then it's very reasonable that we should either redefine VT or really generalize the definition of VT as VT really is not a constant. VT should be the whole thing. This whole thing should be called VT. We'll either redefine or can say expand the definition of VT to represent this whole thing. And the modification is that VT is not a constant for a given device, but it's a function of body bias. All right? So VT is a function of VSB. All right? Specifically, it's equal to that original VT, now we call VT naught. VT naught is represent VT at VSB equal to 0 when there's no body bias. In other words, this is the VT we talked about in the previous few lectures, right? When we don't have any way to apply a body bias, we had only an MOS capacitor with expression for VT. That's VFB plus 2phi-B plus square root of long expression over Cox. We call that VT naught, right? Okay. VT naught plus C depletion over Cox E times VSB. All right? Now we highlight the fact that it's a linear function of VSB. So VT is really equal to VT naught plus a constant times VSB. This we know depends on oxide thickness, doping concentration, work function, no problem. We also know alpha is the ratio of C depletion and C oxide. C oxide, of course, we know what determines that. We also know what determines C depletion, don't we? Right? It's the doping concentration and band bending. Is that right? Yes? All right. Okay. So we know the ratio of these. All right. Now, the fact that VT is a function of VSB is known as the body effect. All right? Sometimes called a body bias effect or body effect. Now, I think most of you probably have heard this, but what you remember perhaps is a more complicated model than what I'm showing you here. You remember VT as some difference between two square root terms containing VSB. Instead, I'm showing you today that VT is really a very simple relation of VSB. In fact, it's a linear function of VSB. All right? This alpha is the ratio of C depletion over Cox. Okay? I'll talk about the difference between this and what you might remember from what you studied before in the next slide. But before we go to there, let me just quickly mention which side we are on. Do we want large alpha or small alpha? In general, for circuit performance, we want small alpha. All right? Small alpha is good. In other words, we don't like to have body effect. If we can get rid of body effect, it's supposed to be a good thing to, all right, for the circuit performance. In other words, we prefer to have small C depletion and large C oxide. Put another way, we want large WD max. We want large WD max, and we want small oxide thickness, T oxide. All right? That statement is certainly true from circuit performance consideration, but later we will see from device scaling point of view, we just cannot tolerate that. All right, we cannot tolerate very large WD max. We'll see why later on. Okay, but right now, I want you to know that alpha is not a good thing. We don't want it. The reason we carry it is because it has some deleterious effect on the performance of the transistor, and we need to know about that. Okay. All right. Now the reason. So let me first plot this VT versus VSB. The model we introduced in the previous page says it's going to look pretty much a straight line. When we don't have any body bias, we have certain threshold voltage, we call that value VT0, right? I use the 0.4 volt as example. It's kind of typical for today's technology. 0.4 volt as threshold voltage when we don't apply any body bias. When we start to apply body bias, the VT increases. Right? So the model we introduced says increases more or less linearly. And if you compare that with experimental data, you will see, yeah, it matches this pretty well. Now, the model that you might have remembered would suggest that this dependence or relationship between VT and VSB is not linear, it's sublinear, right? A square root relationship. So it would look something like that. Now, what's the difference? What has been happening? Well, there are two styles of doping the well or the substrate. One we might call the uniform doping. This is perhaps the shall we say, the more common type of doping until the last few years. But the last few generations of CMOS technology, or maybe I should say in the future, perhaps let me not emphasize too much the past. Let's say today's CMOS technology and in the future, we believe will be built using something called a retrograde body doping. And I will not get into why right now, because that's not the topic for today. This does not give us better IV. We're talking about better IV today. It helps with short channel effect. Let me just tell you that. So we kind of forced to use this retrograde body doping. Now, retrograde body doping has very high doping concentration in the substrate well, but that doping concentration suddenly drops to a very low value. If you look at this thickness, it's only a few hundred angstroms. All right. This, for example, is the doping profile of Intel's 0.18 micron technology. All right. Intel's 0.18 technology from their publications. I got this a curve, and you can see just a few hundred angstroms region that's very lightly doped. Yes. All right. And below that is very heavily doped. It's okay? Now, you tell me, when you look at the retrograde doping profile, what is the WD max? What determines WD max? Is determined by the usual equation of 2Q n sub times 2 phi b, I guess there's epsilon, is determined by that? We know that this was derived for uniform doping, right? So in this retrograde case, which concentration would you put into this n sub? If you use the high n sub, I can tell you the value would be, let's say, 50 angstroms. Does that make sense? Doesn't make sense, right? Because certainly the first 50 angstrom was not doped so high. So what would you give the answer? What is the WD max?
Depth of the shallow region.
It's just the thickness of the slightly doped region, isn't it? And in fact, it's no longer a function of body bias, right? No matter what body bias you apply, the depletion region will end here. Because once you get into a heavily doped substrate, depletion region is very, very small. Very small amount of additional depletion region can take up whatever voltage you apply across this region. See what I'm saying? Okay. If you have been troubled by the PIN type of PN junction analysis of depletion region, you might remember, right? Depletion region does not get into heavily doped portion of the heavily doped part of semiconductor. Depletion region will end where the semiconductor doping becomes very heavy. Is that right? So that explains what we see before. The difference between the linear relationship and this nonlinear relationship is that nonlinear relationship assumes that WD max, or that depletion region, is increasing with is a function of body bias. As we change the body bias, depletion region grows larger, larger. Whereas this linear relationship is a result of a fixed WD max, which happens to be I think a closer approximation to today's technology, and certainly mathematically give a simpler relationship. You see, when you have fixed the WD max, then the relationship becomes really simple. This is our inversion layer, and we're interested in knowing the charge here at this inversion layer. This inversion layer is controlled by two capacitors. Cox is now a constant, and C depletion is now a constant. That's the important thing. It's not a function of body bias. As a result, there's no reason for them to have any unusual relationship. Both of these would have a linear control of the Q inversion. Is that right? Is that right? And therefore, 1 volt on C depletion would be roughly have the same effect of, let's say, 0.3 volt on the VG, simply because this is a smaller capacitor. That's a larger capacitor. Is that right? So if you put 2 volts on C depletion, that's as if you put out 0.6 volt on the across the C oxide. See what I mean? That's why there's this linear relationship. Right? They're just simple capacitors. Right? Okay? All right. We'll make use of this concept more and more as we go on about this equivalent circuit. That there are 2 gates. One is called C oxide, one is called C depletion. Both are controlling the interface. Okay? All right. So W depletion does not vary with VSB. That makes the problem actually easier. Retrograde doping is popular because it reduces off-state leakage, which will be the topic for next chapter. All right? Any questions about retrograde doping? All right. Now we'll apply a non-zero VDS. All right? Suppose now we apply a VDS. Again, imagine this inversion layer as a very thin conductive sheet. Now the potential along the inversion layer will no longer be constant. The potential at the source end of the inversion layer is Vs. At the drain end, the potential is Vd, right? In between, of course, somewhere between Vs and Vd. Let's call that potential along this inversion layer or the channel, call that Vc. Okay? We call the channel voltage Vc. Vc is equal to Vs at the source end and equal to Vd at the drain end. Is that right? That defines, explains what Vc, what we're talking about is Vc. All right? Vc is a function of x, of course, right? Vc is a function of x, yeah? X varies between 0 and L. Is okay? So if we just pick any point, x, where Vc is equal to Vc, now what is the inversion charge at that point? Okay? So now you have to think, we have a capacitor now. We have a Vg here. We have a Vb here. Now this channel potential is forced to be, we force this electrode to Vc. All right? It's forced to Vc. Now I want to know what's the charge density at that electrode, that imaginary electrode, which is our inversion layer, which may not be that imaginary when you consider it's a very good conducting layer, so perhaps I should not call it an imaginary electrode, it's a real electrode. So what's the charge density at this electrode that we call the inversion layer? All right? Okay? Knowing that it's coupled to Vg through Cox and coupled through Vb through C depletion. Okay? Now, do you think this makes sense? It's equal to Cox times Vgs minus VCS. VCS, again, just to clarify this VC, we use the source as a reference, all right? Okay, so every voltage has a reference, all right? So VGS minus VCS minus VT0, all right? Let's just look at this part, see if it makes sense. The first 3 terms. VGS minus VCS minus VT0. What is VGS minus VCS? That is the voltage across the top capacitor, isn't that right? That makes sense, right? The charge on the on this inversion layer should be proportional to Cox or equal to Cox times Vg minus Vc, right? That's what this first 2 terms is about, Vg minus Vc. Is that right? Now, what about minus Vt? Well, minus Vt is because this capacitor has an offset, right? We have talked about Q equal to Vg minus Vt. We have seen that before. Is that right? All right. The next part, and there should be another parenthesis here. Okay. Another parenthesis here. Another part, C ox E times alpha. C ox E times alpha, that product, if you remember what alpha is the ratio of C depletion over C ox E, all right, from the previous slide. Yes? So Cox times alpha really is the whole thing is just the C depletion. All right. So if I, just concentrate on this, it's talking about C depletion. All right. Okay. C depletion times VSB plus VCS. Now, does that make sense? Okay. What are we talking about? We're talking about the easiest way to think is that the top gate already induces a inversion layer. All right. Now you truly have a very physical electrode, which is at the potential that's VCS. All right. Now let's think we have a capacitor on the bottom with VB on the other side of this bottom capacitor. Now how much charge will be induced in this inversion layer as a result of this VB? That should be equal to C depletion, right? Times the voltage across this capacitor, which is VSB plus VCS. Okay, let's see what we're talking about. What is VSB plus VCS? If you look at that, do you agree this really is just, let's see, did I do this right? It's VCS, is that right? VCS. VCB, I'm sorry. It takes you a while to see. VCS plus VS, well, I'll take a little time. VCS plus VSB is the same as VCS minus, I'm sorry, this is good enough. I guess you can see from there right away. CS, C to S plus S to B give you C to B voltage. Is that right? 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 So the charge on the C side of the capacitor, channel side, is simply equal to capacitance times VCB. Does that make sense? Is that right? Okay. So it's really simpler than it needs to be. Unfortunately, we put them in this way because we don't talk about VCB, we talk about VCS, we talk about VSB, right? So it looks complicated. It's really quite simple. All right. But we'll try to make it simple as we collect some terms next. So it's minus Cox VGS minus VCS, no change. VT0 plus alpha VSB plus this term together with VT0 minus alpha times VCS. Now VT0 plus alpha VSB is equal to what? VT0 plus alpha VSB is equal to? It's equal to our new VT. Is that right? We defined as new VT, right? VT is a linear function, VSB. Yes? Yeah? Right? Okay. So that makes it easy. So VGS minus VCS minus alpha VCS. Yeah? So minus 1 plus alpha times VCS. And we define 1 plus alpha as M. So it becomes minus M VCS minus VT. So now we have expression. It's not too complicated anymore. Q inversion equal to Cox times VGS minus MVC minus VT. Now you probably find this very familiar if I take this M away. Yeah? This is VGS minus VC minus VT. So I would like to ask you just carry this M, all right? This is more accurate model, which includes the backgate effect. And backgate is getting to be more and more important, and in fact has always been important, so maybe it's not more important with that manner, but certainly it's very useful to keep backgate in mind from the beginning as we understand the MOS transistor. So M is equal to 1 plus alpha, which is 1 plus the ratio of C depletion to C oxide, and in terms of thickness will be 3 times Tox over WD max. All right? As you can see, the ratio of the capacitances is just the ratio of the thicknesses of those top and bottom gates. Right? Is that right? Where do you think this 3 comes from? Dielectric constant, very good. Silicon has 3 times higher dielectric constant than oxide. All right. So if we have a depletion layer thickness that's exactly 3 times thicker than the oxide thickness, then these 2 capacitors will be equal. That the back gate will have the same coupling to the channel as the top gate. Alpha will be equal to 1, M will be equal to 2. That is considered a bad design for transistor because actually hurts our transistor current. We will see that pretty soon. That's why I want to carry it. On the other hand, it's considered a very good design for the short channel effect. So we're always going to be dealing with this trade-off, all right? Today, seems that we can perhaps take a 0.2 of alpha that may be sufficient for the short channel effect, and we may have to deal with a little larger alpha in the future. Okay, so any question with this Q inversion? Cox times Vg minus mVc minus Vt. This m is called the body effect factor or the bulk charge factor. In SPICE model, this sometimes is called A bulk, all right? If you happen to remember that term in your SPICE simulation model, then you know we're talking about the same thing here. It's called M, all right? Bulk factor or the bulk charge factor or body effect factor, M. All right. Next, we're ready to derive an IV equation. And this part is the same as what you may remember from the first time you see the IV curve derived, except we're going to carry that M, the body charge factor, with us, okay, a bulk charge factor with us. IDS is equal to W times Q inversion times velocity. W is the width of the transistor. Width is the other dimension of L. L is the channel length, and the width is the dimension perpendicular to this piece of paper, to the slide, yeah? That's the width dimension of the transistor. Clearly, current is proportional to W, and it's proportional to charge density times velocity, all right? And the units will work out just fine if you put the numbers in. The units for Q inversion. By the way, what's the unit dimension for Q inversion? What is it? What do you think it is? Coulomb per what? Centimeter square. Very good. Not centimeter cube, but centimeter square. All right. And what's the dimension for W? It's centimeter. What's the dimension for velocity? Will be centimeter per second. Is that right? So you see centimeter cancels out centimeter square. We have Coulomb per second, and that is ampere, right? So that's current. It's just right. All right. So current is equal to W times Q inversion times velocity. W times in Q inversion. What's Q inversion? It's equal to C oxide VGS minus MVCS minus VT. That's the Q inversion. Is that right? This is the Q inversion from the previous slide. Yes? Now, what's the velocity? Velocity is equal to mu times electric field, dVCS dx. That's electric field. Is it okay? All right. What about the sign? What happened to the minus sign of the Q inversion? It will cancel the minus sign in the velocity also. All right. Okay. All right. Next, we do integration. Integrate both left-hand side and right-hand side. Take the dx term, multiply it to both left and right-hand side. So left-hand side, we have IDS dx. We integrate that from 0 to L. Right-hand side, we have this whole thing integrated with VCS from 0 to VDS, because VCS is equal to 0 at source, VCS equal to VDS at the drain. Okay? Now we can carry out this left-hand side integration very easily. We get IDS times L. Yes, question?
Is the electron mobility constant throughout the channel?
It's not. Electron mobility is equal to this, and we did not assume dVCS dx or electric field to be a constant. In fact, we could even derive expression for VCS as function of x. I'll briefly point that out, how to do that. All right? Okay. Let me just briefly point out how to do that right now. Well, let me finish carrying this out, so you will see. All right. So left-hand side, then I'll point it out how to get the VCS as function of x. Let's finish this. Left-hand side, integrate from 0 to L gives us IDS times L. Right-hand side, we have the W, Cox, mu, electron at surface. We have nothing, there's no change to that. Now we look at what we have here, right? We have a term called VGS times VCS. We take the two limits of integration. We simply get VGS times VDS. Is that right? Is that right? And we have that here, VGS times VDS. Okay? Similarly, this is minus VT will give us term that's minus VT times VDS. And right here, minus VT times VDS. Okay? Now this term is a little bit more complicated. After we integrate this term, we get minus MVCS square over 2. Right? And we have to evaluate that between 0 and VDS. So what we get is minus MVDS square over 2. Minus MVDS square over 2. And we got it here. Minus MVDS square over 2. All right? And just to emphasize this equation and put in the final form, divide the L to the right-hand side, we'll get IDS equal to W over L, Cox, mu E, VGS, minus VT, minus M over 2 VDS times VDS. I put it in a box. That means I want you to remember this, memorize this. This is no different from what you have seen before, with the exception that we carry the M here, but it's a small, simple enough of a modification, and I think you have no objection to carry that with you from this point on, all right? So current is equal to W proportional to W, inverse proportional to L, Cox times mu times VGS minus VT, all right? Minus MVDS over 2 times VD, okay? There's a simple interpretation for this. What we're talking about is VDS over L gives us the average electric field. So average electric field times mu gives us the velocity, right? Velocity times W times charge give us the current. The charge is equal to C times VG minus VD. I'm sorry, VG minus VT, that's fine. We know what VT is. And what is 1/2 of VDS? Why not VDS? Well, that's because it's average between VDS and 0. So kind of in the middle, the average potential happens to be VDS over 2, right? We did not make that approximation, just the integration happens to give us a result. We're not interpreting that result, all right? Can be interpreted as taking the average between 0 and VDS. Is that right? The M's comes in because there is a body back bias effect. All right? So let's just zero in on this body bias effect, the backgate effect, or so-called the bulk charge effect. Let's look at zeroing on the bulk charge effect. Is the bulk charge effect helping us to get large ID, or is reducing ID? The bulk charge effect. When there's a large bulk charge effect, does that mean we have a large M, we have M equal to 0? Or M equal to 1? M equal to 1 means no bulk charge effect. All right, if you look back to the previous slide, M equal to 1 means no bulk charge effect, means the backgate is not there. M is 1. All right, that gives you the usual equation, simplest equation. When M is large, it means we have strong bulk effect, bulk charge effect. All right, and this is said, well, let me just ask you, knowing that now, does the bulk charge effect help increase IDS or make IDS smaller? Make it larger or smaller? Bulk charge effect make IDS smaller, all right? Next thing I want you to remember, if you don't know that is we want as large IDS as we can. That's what gives us speed in the circuits. Large IDS is good, small IDS is bad, all right? So with that two together, can you now answer the question, is the bulk charge effect a good thing or bad thing? It's a bad thing. That's why we don't like bulk charge effect. We prefer not to have that back capacitance, all right? If we can get rid of it, that's great. A lot of people don't realize that when they see this retrograde, thinking, that's something we put in to give us a better transistor, give us more current, make the circuit faster. Well, it doesn't quite do that, all right? At least doesn't do that in this manner. And but it does allow us to make the gate smaller because help us suppress the short channel effect, okay? But it actually cuts down on the IDS, so we don't like that, right? Knowing this, for example, would help you say, hey, is there a way to have the cake and eat it too? Can we suppress short channel effect without hurting the current? Well, certainly knowing there is this trade-off is helpful because it makes you think whether you can do it or not. And later as the course goes on, we will see whether there are some things we can do about it or not. But let me tell you right now, there's nothing simple that we can do about that. It seems to be fairly a fundamental trade-off there, okay? And in order to understand that, we have to understand short channel effect, of course. Why is that fundamental? To have that back gate. Okay, so any question about this IV characteristics? It's a simple model. Is it accurate? Well, accurate or inaccurate is all relative, so I don't want to color you very much. But let me say that it's not accurate in general. Certainly, this is not a model we can use to estimate the transistor current today. If you do that, you could easily be off by a factor of 2 or 3, actually. You can play games by saying everything you don't know is more mobility you don't know, but we don't think that's the right way of thinking about it. And we'll talk about a more accurate model in Chapter 5. Nonetheless, this is still a very important model because it captures a lot of physics. Anytime you have a new question about MOS transistors, I think it's advisable to come back to this level, think about it, all right? But we will introduce even more accurate models as we move on, okay? Especially with this addition of the body effect or the bulk charge effect. I don't like the term body charge effect. I think the backgate effect is actually a better name. I'll explain in a minute. This becomes even more useful model than without that M, right? Okay, why do I like this body charge effect? You can see now that this term kind of comes from the days of the uniform doping. The reason we're losing some of these current is because the gate voltage is not all used to induce charge at the inversion layer. Some of the gate voltage is occupied to induce some depletion layer charge. That charge in the depletion region, so we call that the bulk charge effect. But now you know the depletion layer cannot increase, right? Right? It's not like depletion layer expanding. It's as if we had a gate, almost as if there was a metal right underneath a fixed capacitor. In that case, do we really want to call that, bulk charge, or is it better just to think of this as a back gate or a back capacitor? So bulk charge is not, I think, that descriptive a name for the phenomena this is describing. Nonetheless, that's still the standard term. So the bulk charge effect, all right? Okay, so if we make a plot of that equation, plot it, what you get is this, ID versus VD. Has several curves. They, each of them will saturate at a certain VDS, and the saturation current increases with VGS, with increasing VGS. And this is known as the basic MOSFET IV characteristics. It's okay? Now, if you take the equation from the previous slide, that IDS equation, IDS is a function of VGS and VDS. Okay? If you differentiate that with respect to VDS and set that to 0, you are going to find the differential gives us this. And by setting to that 0, gives us VDS is equal to VGS minus VT over M. In other words, at that particular VDS, when VDS is equal to this quantity, the IV curve becomes flat. And that's what we call the saturation voltage, drain saturation voltage, all right? So this is the drain saturation voltage, VD sat. And M is a result of the body effect, I would say, all right? Okay. Okay. So this explains partially why in real devices, VD sat is always smaller than VGS minus VT. It's never VGS minus VT, always smaller than that, first by this factor, and we'll see other reasons later why VD sat is even smaller than this quantity. This equation would predict. Okay, any questions about saturation voltage? All right. Now I want to take a little time trying to explain why the current saturates at VD sat and what happens beyond this. Why is the current constant? All right, how to understand it and what is the situation in the channel in the saturation region? Okay. So the first thing I do is I will answer a question that was brought up a little earlier. That is, what is channel potential as function of x? We did not assume that the channel potential varies linearly between source and drain. We didn't assume the electric field is a constant between source and drain. Instead, the field is smaller near the source and larger near the drain. Now, how do we get this curve? We get this curve from that integration earlier. I will copy that for you right now. We have this integration, if you remember, I ds dx is equal to WC mu Vg minus MVC minus VT dVc. You may remember we integrated this equation when we derived the IV characteristics. Yes? What were the limits of integration we used? What did we use? From 0 to what? To L. And here is from 0 to VDS. Now, if instead of that we integrate only from 0 to x, we of course can do that, right? Then here should be from 0 to what? Just VC, right? Right? Not all the way to VDS. VC at a particular point in Vx. Turns out, left-hand side can still be integrated. It's just equal to IDS times x. You see that? Right? Left-hand side also can be integrated, and this time will involve some VC square term. A square term, right? You see that? Now just use the polynomial formula. We can write VC as function of x. Just solve for the x, right? You see that? Yeah? If you solve it, this is what you get. VC as function of x, like that. All right? This makes a lot of sense. It's self-consistent, this particular. Self-consistent in what way? In this way. There's only one solution, only one shape of this curve that will satisfy the following relationship, following two relationship. That is, first, Q inversion, if we use Q inversion, well, in fact, I will say only one CS versus L that will satisfy this fact, that the current must be constant between source and drain. The current must be a constant between source and drain. That's current continuity. Current must be constant between source and drain, right? Okay. Why would this VC versus X ensure that current is continuous and constant between source and drain? Well, that's because current is equal to W times Q inversion times velocity. Now, it just so happens we're making, because electric potential is increasing from source and drain, as a result, the Q inversion is decreasing from source to drain. Why? Because as we move from source and drain, the bottom capacitor's potential is increasing from 0 to VDS, right? Therefore, the voltage across Cox is decreasing. And therefore, the capacitance charge is decreasing, right? So for a given shape of V versus X, that fix the shape of Q versus X. See that? For a given shape of VC versus X, we have a fixed shape of Q or X. Similarly, the velocity is also determined by the shape of this V versus X curve. Is that right? Because it's equal to mobility times dVc dx. Right? And it just happens if you multiply the slope of that curve, VC curve, with this Q inversion, you end up with constant. All right? So that's what determines this particular potential distribution, and that can be mathematically derived if we make that integration this way. Okay? We don't often use it, therefore we usually don't talk about integrating this, but it can be done. Okay, so for now, there's no need to memorize there's such an equation, but just know, well, no need to know what the equation is, but just know there's a solution to the potential, and it's generally of this shape. Okay, slope gradually increase. And this particular shape creates a particular Q inversion wave profile, which gives us ID. Okay? Now, this, of course, analysis is okay for any VD equal than or less than VD set. We can always draw a series of curves for a particular given VDS. So I want you to focus on a particular set of curve made for VDS equal to VD set, right at VD set. Beyond that, the curve may have to change shape because our analysis did not assume or does not account for the fact there may be some kind of thing called, maybe we're going to call it the pinch-off region, right? It assumes there's an inversion layer continuous from source and drain. The charge density on the inversion layer may be non-uniform, but it's always inversion layer. So this analysis is good for any VDS up to VD set. So let's focus on this set of curve, which I happen to have plotted for you, that is at VDS equal to VD set, right? At that point, for that particular VDS, Q inversion is 0 at the drain, right? For smaller VDS, Q inversion would not be 0 at the drain, right? Will be smaller than at the source, will be non-zero. But when VDS is equal to VD set, will be exactly 0, right? At that point, the current has a particular name called ID set. Yes? Yeah? Okay. So with this as the benchmark, I'm going to ask you to draw the same series of curve for a condition of VD set is larger than VDS is larger than VD set. Why don't you just think about it for a moment, then we'll draw it together, all right? So this is the benchmark. If on the same set of curve, you are asked to make a new plot for VDS equal to VD set plus 1 volt, let's say, how would you do that? How would you do it such that it does not violate any of the things we talked about? For example, Q inversion may look like that, and current must still be continuous, right? You may conclude that current should not be equal to ID set, and that's fine. That's the exercise, purpose of this exercise. Of course, you probably predict that I'm expecting you to conclude that it should be this equal to ID set. When VDS is larger than VD set, current remains ID set, does not increase beyond ID set. Think about how you would draw it. Okay. So next slide shows you the solution to this question. Left-hand side shows the same 3 benchmark curves that we just looked at in previous slide. The right-hand side shows you how to draw these 3 curves when VDS is larger than VD set. Here's the solution. Solution says, okay, we know the left-hand side curve are the correct answer. It's a quite unique answer for VDS equal to VD set. If we change the shape a little bit, it just won't work, right? That's why there's a unique ID called ID set. Let's try this as a solution, see if it works or not. That is, the curves remain exactly the same, absolutely no change. It's just that extra voltage The difference between VDS and VDSat is dropped in a very narrow range, and you all know what we call that region. We call that a pinch-off region. It's dropped in a very narrow region. And we'd assume that region is so narrow, it's negligible compared to the channel length L, right? If we make that assumption, then these three curves doesn't have to change at all. Is that right? Right? Doesn't have to change at all. And we know these three curves are very unique. They satisfy a particular relationship to allow current to be continuous, and that current happen to be equal ID set. Now, this pinch-off region, does that block the flow of current? Block the flow of current? After all, there's a concept of pinch-off region is a depletion region. Does that block the current flow? It doesn't. Just look at the energy band diagram. Here I'm drawing the energy band diagram for this curve. Of course, as you know, energy band diagram is just that potential profile flipped around, the mirror image of the potential profile. Is that right? So we have here we just draw the EC at the source, EC at the drain. We show almost no barrier between the source and channel. This is because we're assuming strong inversion, right? The electron density is very high. The VG has bent the EC almost as low as the conduction band. In other words, the carrier concentration, electron concentration in the channel at the source is almost equal to the source doping concentration, right? Okay. And the electron, therefore, flows down this potential hill happily until they reach the drain. There's no problem for this benchmark case when VDS is equal to VDSat. For the case of VDS larger than VDSat, again, the energy band diagram is the mirror image of that. I guess this is not drawn very well. We really prefer to shift this axis, right, to so that the whole curve is shifted. I'm asking Kevin to shift this for me, right, to I guess, line up here. So that's clear what they're talking about, all right? So there's no difference, except there's now a sudden big extra potential drop that happens to be equal to VDS minus VDSat. Is that right? Does this hinder the flow of electrons in any way? No, it doesn't. The only thing it does is to give the electron a lot of energy. So it might give us some problems like hot carrier problems, things like that. We'll talk about that later in the course, right? But certainly doesn't have any impact on the current. The current is determined by what's going on here. Is that right? One concept is that, you know, the flow, water flow in a rate of water flow in a waterfall, let's say, right? It's not determined by the head of that waterfall. It doesn't matter whether that waterfall is 100 feet tall or 300 feet tall. It's determined by the slope and maybe the depths of the river feeding the waterfall. You see that point, right? The same idea here, all right? So that is why when we go beyond VDSat, the current doesn't change anymore. The current simply stays constant, all right? Does not decrease, does not increase, but remains constant, all right? So we have something called a VDSat, and we have something called IDSat, all right? VDSat we have already seen before. It's equal to, let me write down one more time. VDSat is equal to VGS minus VT divided by N. Is there a question? Yes.
Yeah. Is there a reason why, I guess, Q inversion goes to 0 at L? Why couldn't you shift the curves so that, I guess, the pinch-off occurs before L?
Very good. That is the approximation we made. The question is that why do we force this point happen L? Why can we not do something like that? All right. Why don't we do something like that? Shift it a little bit, right? Absolutely right. This is a more accurate version of the model, and it's called the channel length modulation, and we will talk about that in the next chapter. But right now, let's assume that this L is very large and this channel length modulation is very small, so we can ignore that, all right? So the remaining question is what distance is needed for there to be such a voltage drop, right, for this voltage to be dropped. The way we drew it definitely is non-physical because it will give us an infinite electric field. So what then is a more physical model for this? Some of you might have attempted to model this using a p-n junction. You know, you have a certain volt drop across p-n junction. If you know the body doping concentration, can you estimate a pinch-off region thickness? Well, it turns out that's very, very much off the mark. You get way too large an estimate, and we'll introduce a model of this in the next chapter about channel length modulation. All right, channel length modulation turns out to be quite important in the behavior of transistors in analog circuit because it determines the gain of the transistor. The small slope of this portion of the curve is very important for the analog applications. So we'll talk about that. All right, so we already know VD set is equal to VGS minus VT over M. Now ID set, in other words, when we substitute this quantity for the VD S in the ID expression, then we get an expression for ID set. That's equal to W over 2mL Cox mu VG minus VT squared. So this is very similar to what you have remembered before. W over 2L C mu Vg minus Vt squared, well-known quadratic relationship. What's new is this M, so remember that, all right? So this bulk charge effect or the body effect gives us, or the backgate effect gives us, reduces the current at any Vd and any Vg. All right? Okay. Questions? All right. Let's see. The next two slides, I think we can skip them. It's just another look at what we have already looked at, I think. Well, I'll still flash them down here. Let's see if there's any questions maybe about these. All right. Here it just indicate that the pinch-off region, let's see, maybe we won't, okay, that's all right. I don't think there's anything new here that I have not yet talked about on this slide. This slide, I also think we have already talked about everything. All right, okay, good, all right. So picture is the thing that at point A and point B, the potential profile, the velocity profile, and the current are all the same at A and B, and C as well, all right? The only difference is that at point B and C, there is a small pinch-off region where that extra voltage is dissipated, okay? So that's the picture. Okay, so for example, if I ask you, what is the potential at the bias point B, right? What is the potential in the channel at the beginning of the pinch-off region, at this point where I draw a cross? Yeah. What is the channel potential, channel voltage at the beginning of pinch-off region? Hopefully, you will be able to answer. At this point, VCS is equal to VD set. All right. Potential will increase across the pinch-off region from VD set on one end to VDS at the other end, from VD set at one end to VD set to VDS at the other end, right? At the beginning of the pinch-off region, it's VD set. Yes? Right? Now answer the same question for bias point C. What is the channel potential at the beginning of the pinch-off region at bias point C? VDS? VD set? Would you agree? It's VD set, right? It's also VD set. Okay, very good. Any other questions about today's discussion, today's lecture? All right, yes, please.
I have a question about the last slide.
Sure, the one with the This one?
I
Okay.
wonder how to draw the Fermi level for the second graph on the left.
Ah, very good. All right. So let's spend a little time looking at this. I know your question is about Fermi level, but I need to explain this a little bit more. All right. Think of this as the source and the channel. Looking at left-hand side first. Think of this as a source and channel. All right. And the drain, I'm not showing the drain in this diagram. Okay. So source is M plus. Therefore, we draw the energy band diagram very close to the Fermi level. I'm sorry, draw the Fermi level close to EC. It's actually not close enough, but you know what we're trying to do. We're trying to draw a Fermi level close to EC, yeah? And the substrate is p-type. What we are drawing here, you probably would guess, is appropriate. Maybe you guess we're assuming. We did this actually for the so-called flat band condition. All right, may not be clear to you, but it's for flat band. If we draw this for flat band condition, then the Fermi level for the channel portion is exactly where you would be in an equilibrium p-type semiconductor. That's kind of where you'll see. Okay, all right. Now, just for fun, maybe, well, I won't answer anybody. Next, the bottom diagram is for the case when we apply Vg equal to Vt. Now, you can tell that's the case because you noticed in this bottom case, EC is pretty close to a for the Fermi level now. Means we already have an inversion layer there. Is that right? Yeah? So that's the energy band diagram. Okay? All right? Now, can you relate this diagram to something that we drew in the last few lectures a lot? That's this, right? At Vg equal to Vt, Fermi level is close to EC, like that, right? So it's this band bending that's responsible for the difference between the top diagram and the bottom diagram. We're not looking at the source side. Source side is not affected by the bias, yeah? But the channel portion of this energy band diagram is very much affected by this. Yes? In the flat band case, we don't have this band bending. That's why we it's the band bending that's making this energy band diagram change from this to this. All right? So this is another way of looking at the effect of the band bending. All right? Okay, great. What I want to emphasize is that what's allowing current to flow, of course, is that now there's inversion layer. Another way to say it is that now the barrier for the electrons is removed. The reason we did not have current flowing between source and drain is because it's barrier. Although we have a lot of electrons in the source, they cannot go through the channel, get to the drain because of the barrier. When Vg is large enough, this barrier is low enough, now current will start to flow. All right? This concept is particularly useful when you talk about leakage current in the off state. For on state, we usually don't think that way, but I actually think it's good to think that way. It certainly gives a unified way of thinking. So let's look again. So if you now add the drain to it, just the source, channel, and drain, at Vg equal to or larger than Vt, now we know there's no barrier to electron flow. But for the top figure, I still made Vds equal to 0. So therefore, you won't have current flow. If we now apply some voltage, now current will flow, right? And if we want to really draw this well, we probably should not show, it's perfectly flat portion, which means no field. If there's no field, there will be no current, of course. I really meant to show there's actually already some field right at the source, right? That's what kind of we expect to see, right? So this is the picture at Vg larger than Vt and Vd larger than Vs. Okay. Now back to your question: how do you draw the energy band? How do you draw the Fermi level? Drawing a Fermi level in a non-equilibrium case is always difficult. Now, what does equilibrium mean? Well, when there's no voltage applied throughout the system, then it's easy. It's an equilibrium. We all know that. Even in this case, we can still say it's equilibrium, because even though there's voltage applied to the gate, but just because the gate is such a good insulator, we don't have any current flow, we don't have energy exchange, that's equilibrium. All right? All right? So drawing energy band diagram is also simple. There's one energy band diagram. Okay? Anytime you have current flow, we know we're not at equilibrium. When we're not at equilibrium, drawing energy band diagram becomes somewhat of an iffy proposal. You almost have to do this iteratively, make some guess and say if it makes sense or not. And if you understand device physics a lot, then you can draw the energy band diagram. It's not like there's a certain rule you can follow to draw the energy band diagram and that immediately tell you how the transistor operates. It doesn't quite work. It's almost work backwards. So the usefulness of the concept at Fermi level is somewhat limited. So for that reason, we probably should not be too concerned about how to draw the energy band diagram when it's not so useful. That's why sometimes you see energy, Fermi level, I mean, is not drawn because it's not so useful. That's why you see that's omitted. But if you do want to draw it, I think it's going to look something like that. And I'll draw it and then I'll explain to you what we're doing here. Okay, let's see, it's going to be, there will be two Fermi level. That's always the difficult problem with that. Let me think what's the best way of doing this. Yeah, as you can see, I've never done it, but okay, it will be like that. Okay, it's surprising to you, but I'll tell you what it may actually will look something like this before coming up. Yeah. Okay. So what I'm drawing to you is what I will call the quasi-Fermi level for electrons, and you will define that as this way. Just because I wrote this way, so I'll do it. Log of how do I do this? Let's see. How do I do this? Let me think. Log, yeah, I'll do it this way. Log, let me think. I'll use, okay, I'll do it this way. NC over N, electron concentration. And this will be, EFN will be EC minus that, let me think. Yeah, EC minus that, all right. So this will be the conduction band edge minus this. In other words, we're saying the electron concentration always follows this. NC exponential minus EC minus EFN, all right? Not just EF, but EFN over KT. I guess because I'm using energy, I don't need this Q here, okay? So this is the way to define the quasi-Fermi level, and with that definition, one will be able to draw this. This is very much not useful, very much useless when in this portion. But in this portion, kind of still a little bit useful, for example. So I'll emphasize this part and see what I tell you. For example, if you see this, then you immediately can tell, in the channel, actually electron concentration is a little bit less than the electron concentration in the N plus doped source. Why? Because Fermi level is farther away from EC in the channel than in the source. Can you see that? Is that right? That's a little useful because we actually know separately that quasi-Fermi level also should be more or less continuous, cannot go through very large jumps. Quasi-Fermi level has to be pretty smooth because quasi-Fermi level is kind of proportional, or its gradient is proportional to current density. So if current density doesn't change a lot, then this quasi-Fermi level should not change very rapidly. So we know this is going to be smooth. Immediately, then we can tell there's going to be a little bit difference, a jump in the carrier concentration. Or put another way, if for some other reason you first know the carrier concentration, such as from the first few chapters, you know the carrier concentration here, then from this you can tell there's actually a small energy barrier for whatever subtle things it might do. You can tell that. So. Fermi level in non-equilibrium condition is not always very helpful. Sometimes it is, but often it's not very useful. Okay, let's take 10 minutes break and come back for the discussion session.